Hello guys, and welcome to our first video note section for our second semester, where we are beginning in chapter 4 and on the concept of antiderivatives. So what is an antiderivative? Well, this definition from our textbook basically says that, let's say you have a function f. We say that f is an antiderivative of another function. I'm using uppercase f for the antiderivative and lowercase f for the other function. So uppercase f is an antiderivative of lowercase f on an interval if the derivative of uppercase f is equal to lowercase f for all values of x in that particular interval. Now, what that basically means is if I'm saying, oh, show me the antiderivative of lowercase f, I'm asking you to think backwards to what function did I take the derivative of that's leaving me with this new function. So you can also think of this as before the derivative. Antiderivative means before derivative. Before you took the derivative, what was that function? What function did I take the derivative of to yield this new function? So here's some examples down here of my lowercase f. So let's say I have the function 3x squared. The antiderivative, or the before derivative of that function, would be x to the third. Because if I take the derivative of x to the third, right, if I take the derivative of that, I'd bring the 3 down in front, I would subtract 1 from the power, I would get 3x squared. So this is the derivative of x cubed, therefore x cubed is the antiderivative of 3x squared. Another example, let's say I have the function negative sine x. Okay, so what's the antiderivative of negative sine x? It's whatever function I must have taken the derivative of to get negative sine x. So you'd have to think backwards. Negative sine x is the derivative of what function? What was the function before the derivative was taken to get negative sine x? And the answer for that is cosine, because if you take the derivative of cosine, it leaves you with a negative sign. Now, I want you to notice here that we're saying f is called an antiderivative of f rather than the antiderivative of f, because when you take the derivative of a constant, you get 0. So I could have had the function x cubed plus 5 earlier, right? If I take the derivative of x cubed plus 5, it too will equal 3x squared because the derivative of 5 is 0. So because of the fact that the derivative of a constant is 0, and when we go backward to take the antiderivative, we have to remember that the constant could be different. Because again, if I take the derivative of this example, x cubed minus 100, I get, again, 3x squared plus 0, which equals 3x squared. So this function and this function and this function all have the same derivative. The derivative of each of those functions is equal to 3x squared, because whether there's no constant or whether the constant is different, they all go to 0 when you take the derivative. So we have to remember when we go backward, when we're taking the antiderivative, to add a c, which represents any generic constant at the end of our function, to represent the family of functions, if you will, that are the antiderivative of f. So this concept is kind of summarized up here in this theorem 4.1, the representation of antiderivatives. So this is basically saying that if f is an antiderivative of a function over an interval, then g is an antiderivative of that same function if it's of this form, the antiderivative of lowercase f plus c, right? Any function that equals the antiderivative plus c is also considered an antiderivative of that same lowercase function f. So this just kind of reinforces the idea that any function with an addition of a constant, any constant, is also considered an antiderivative of lowercase f. And here I just have some examples again here. So basically, an antiderivative, or the representation of the antiderivative of 3x squared, would be this function, right? This is the function that we take the derivative of to get 3x squared, plus a constant, because if I take the derivative of that, I would get the derivative of x cubed, which is 3x squared by the power rule, plus 0. And then similarly here, the antiderivative of negative sign is cosine, right? That's the function who, if you take the derivative of it, gives you negative sign. And then if you add c to that, that just kind of represents all the possible antiderivatives of this lowercase function, f over here. Now, another term we use when finding antiderivatives is called the indefinite integral. An indefinite integral looks like this. It looks like a stretched out S symbol, and there's no number at the bottom or the top. Basically, it's an integral sign without any limits to it, so it's indefinite. That's why we call it indefinite integral. You will notice a dx inside these indefinite integrals, and that is referring to the variable of integration. So this is saying I'm taking the integral of f of x with respect to x. That's kind of what that means. And the result of that integral would be the antiderivative. So when you're taking an indefinite integral of a function, this is basically saying find the antiderivative of this lowercase f with respect to x. And so you think backwards. You have to think backwards and go, okay, what function did I take the derivative of to get this? Whatever that function is, that's the answer to your indefinite integral. And then you have to always remember to add c, because when you take the derivative of a constant, you get 0. So you won't see it represented in the derivative function. So you have to just remember that there could have been a constant there and add it to your antiderivative function. So going back to our two functions that we've been working with, if I ask you to integrate, right? To integrate, or integration, is the process of taking the antiderivative or finding the antiderivative of a function. So this is saying find the integral of, or integrate 3x squared dx. And so what you do is you find the antiderivative. What function do I take the derivative of to get 3x squared, and add c? Same here. This is saying take the integral of, or integrate negative sine x dx, or find the antiderivative of negative sine x dx. What is that? Oh, that's cosine x plus a constant, right? The function that if I take the derivative of it gives me negative sine, so the antiderivative, cosine, plus a constant. So to do that, right, we need some basic rules. Just like when we were taking derivatives, we had basic derivative rules. We also have basic integration rules, which is basically undoing those derivative rules. It's the opposite, basically. So since the derivative of a constant is 0, then the antiderivative of 0, or the integral of 0, is a constant. So we kind of start there. We have a constant multiple rule for integration. If you have a constant, so notice that here k is just representing a constant, and it's being multiplied to a function, the integration rule for that says you can pull the constant out of the integral. So you can take the k out of the integral and just multiply it to the result of the integral. You can just multiply it to the antiderivative. Now, if you have just a constant, right, so not 0, but some constant number, then we understand that the antiderivative of that must be a linear function, must have been an x to the first power, because only linear functions have derivatives that are constant, right? This would have been the slope of this line. So you can also think of it this way. The derivative of a constant times x to the first power, and I'll go ahead and add the c. So derivative of kx is just k, and then the derivative of this constant without an x is just 0. So if your derivative is a constant number, it must have been the slope of a line of a linear function. Therefore, the antiderivative would be that constant times x to the first, and then, of course, plus your c, which is your constant of integration. This is the sum and difference rule for integrals, and it basically says if you are adding or subtracting two functions inside an integral, so it's basically saying take the antiderivative of f of x plus g of x, or f of x minus g of x, you can go ahead and separate those integrals. You can separate the integral over that plus or minus. You can integrate f separately, integrate g separately, and then just add the result. For our trig integration rules, it's basically going backward from our derivative rules. So because the derivative of sine is cosine, the antiderivative of cosine is sine. It's just going backwards. Because the derivative of cosine is negative sine, then the antiderivative of sine is negative cosine. So this, you're going to have to really work hard to remember, because when you take the derivatives of sine, that's the one that stays positive, and the derivative of cosine is the one that goes negative, but it's the opposite when you take the antiderivative. The antiderivative of cosine is the positive one. The antiderivative of sine is the negative one. So that's something you'll really have to keep in mind. Here, we know that the derivative of tangent from before was secant squared. So now when we take the antiderivative of secant squared, or the integral of secant squared, that would be tangent plus a constant. Since the derivative of cotangent was negative cosecant squared, then the antiderivative of positive cosecant squared must be negative cotangent, because the sign of cotangent changes when you take the derivative. So I'd have to take the derivative of negative cotangent to get positive cosecant squared, because it would be negative cosecant squared. So remember that one as well. Then because the derivative of secant is secant tan, we have to remember that when we see that in an integral, we think, oh, that's the derivative of secant, therefore the antiderivative of secant tangent is secant plus our constant of integration. And likewise, the derivative of cosecant was negative cosecant cotangent. So if I'm taking the integral of positive cosecant cotangent, then the function that I must have taken the derivative of to get that must have been negative. The derivative of negative cosecant would then be negative cosecant cotangent, which is positive. So we have to remember that fact when we're going backwards. So if we have an integral of positive cosecant cotangent, then that antiderivative must have been negative cosecant x plus our constant of integration. So these integration rules are just the derivative rules backwards. So you'll have to know both really well. Then for anything with an exponent, our exponential integration rules are as follows. So this one here is the power rule for integrals, which is a reverse power rule from the derivative. Now remember, when we do the power rule for a derivative, I'll just do that down here, we would bring the n in front, and then we would subtract 1 from the power. So if I'm going to reverse that, I'm going to need to add that 1 back to the power to go backwards, right? And I'm going to need to cancel out whatever this number was here. So I need to divide it out, because if this is just 1x to the n, and this is the derivative of something, a derivative of a power function specifically, then that means that I must have multiplied something to this. So that's why I need to add a denominator to cancel it out, basically. So this n plus 1 will cancel out whatever constant would have been multiplied in front. And then the adding 1 to the power will undo the subtracting 1 that we do when we take the derivative. So this is undoing the derivative. This is anti-differentiating. So when we're doing the integral of x to the n, we add 1 to the power and divide by it instead of multiply by it and subtract 1. So we do the opposite. This only applies, though, for values of n that are not negative. Make a very special, not negative 1 specifically. Negative 1 specifically. Make a very special note of that, because we do something very different when it's x to the negative 1, right? This is x to the power of negative 1. That is very different. We do not do a reverse power rule, because we do not get 1 over x from taking the derivative of x to a power. Let me just illustrate really quick. Let's suppose I did do the reverse power rule on a 1 over x function. This is what would happen. I would add 1 to the power, so I'd have negative 1 plus 1, and then I would have to divide by that. So I'd have x to the 0 over 0. If I were to use this reverse power rule, which is undefined, right? It's 1 over 0, that does not exist. That's not what the original function was. So when x is to the negative 1 power, we do not do the reverse power rule. Instead, we remember this fact that when you take the derivative of the natural log function, the derivative of ln of x is equal to 1 over x. So we have to remember that this is the derivative of the natural log. Therefore, the natural log is the antiderivative of 1 over x, not this power rule. And then, of course, plus c. The absolute value is there because the inside of a natural log has to stay positive. Because the natural log is undefined for negative values inside, they're not in the domain. And since we're going backwards from this function here where x's were allowed to be negative into the antiderivative where they're not, I have to ensure that my domain stays positive. So that's why the absolute value is here this time and wasn't here this time. Okay, and then when your base is a constant and your variable is the exponent, we have to remember those are exponential functions and had different derivative rules. So they also have different integration rules as well. So this is my favorite function here because when you take the derivative of e to the x, it just equals itself. So it's also its own antiderivative. When you take the antiderivative of e to the x, it also just equals itself and then plus a constant. So the derivative of e to the x is e to the x, and the antiderivative of e to the x is e to the x. It is my favorite. Mi favorito. It's the easiest to remember. Now, a to the x comes in a close second because it's almost like that. You have to remember here that the derivative of a to the x, so when I take the derivative of it, you see that it appears in its own derivative. It was a to the x times ln of a. ln of whatever the base is. So that's the derivative. So if I'm going backwards, if this a to the x is the result of having already taken a derivative and there's no constant there, then that must have meant there was a 1 over ln of a to begin with, so that it would cancel with this ln of a. So this 1 over ln of a is sort of the way of undoing or reversing that action of multiplying by ln of a when you take the derivative. So this part undoes that. And then this a to the x is just there already, right? It appears in its own derivative. So this just cancels out the constant. So the antiderivative rule would be itself, right? Antiderivative of a to the x is itself divided by ln of a versus multiplying by ln of a. So these are all important rules that you will have to remember as you are asked to do different integrals. And so the more you remember the derivative rules, the easier it will be to also remember the antiderivative rules. I do recommend making flashcards for both and quizzing yourself, because the more you do that, the more they'll just be in your brain. Let's work out a few examples. So in example 1 here, we have a simple power function. And I know that because it's just x raised to the negative 3. That's the same thing as 1 over x cubed. So first I rewrite it that way to understand or recognize, oh, I'm going to use this property, the one that has, if I'm taking the antiderivative of x to the n, I add 1 to the power and then divide by whatever that is, and then add my constant of integration. So in this case, my n is negative 3. Right? The n is negative 3. So I'm going to just add 1 to that. So I get negative 2. Divide by that same number. And then kind of simplify here. So this means 1 over x squared, right? So I have negative 1 over 2x squared, and then plus a constant. Because when I take the derivative of this, I would get 1 over x cubed. And then when I take the derivative of c, I would get 0. So this is our antiderivative of 1 over x to the third. Why don't you guys try this one here? So the first thing you want to do here is recognize that the square root of x is just a power function. It's just x to the power of 1/2. And so we could rewrite it that way. We can also pull the 3 out of the integral and not really worry about it until the end. It can just get multiplied in the end to our antiderivative function. And then we just apply the reverse power rule to x to the 1/2. So we add 1 to the power, and then we divide by the power plus 1. So 1/2 plus 1 is 3/2, and I'm dividing by 3/2, which is basically the same thing as multiplying by its reciprocal. Dividing by 3/2 means I'm multiplying by 2/3. Meanwhile, I had my constant of 3/1 that I'm multiplying, so those 3's actually cancel out. And then I'm just left with 2x to the 3/2 and then plus my constant of integration. Don't forget to add your constant of integration. Now, if you're not feeling confident with your answer, you can always check it by finding the derivative. Because what we're essentially saying is that this function is the derivative of 3 root x. Or if I took the derivative of this, I would end up with 3 root x. So we could go ahead and take the derivative of it to check. So to take the derivative of it, I would multiply the power to the 2. So it'd be 2 times 3/2. Bring the power down. And then I would subtract 1 from the power. And then, of course, the derivative of constant is 0. So then these 2's would cancel. And then 3/2 minus 1 is 1/2. So I would end up with 3 left over times x to the 1/2, which is equal to 3 times the square root of x. Check. This really is the derivative of 2 times x to the 3/2 plus c, because if I take the derivative of it, this is what I get. So then this is the antiderivative. The function who, if I take the derivative of it, equals 3 rad x. Now in example 2 here is where I get 3/x. And you can see how it would be tempting to go, oh, that's just integral of 3 times x to the -1. Oh, that's just 3 times integral of x to the -1. This is no problem. Okay, that's just 3 times x to the -1. And you might be like, wait. This isn't working. So just be careful. When it's x to the -1, we do not use reverse power rule. We use the natural log. So first I'm going to take the 3 out. This is 1/x dx. And then I'm going to remember that 1/x is the derivative of ln, right? The derivative of ln of x is equal to 1/x. So then this is just 3 times that. So this will be 3 times ln of the absolute value of x plus c. And that is my antiderivative of 3/x because it was to the first power in the denominator. That's a derivative of natural log of x. Why don't you try this one here? So for this one, we can start by noticing it's got a constant of integration and just pull that out. This is 2 times the integral of sine. And then we have to think, what function do I take the derivative of that would equal positive sine? That function must have been negative cosine because the derivative of positive cosine is negative sine. So the only way I'd have a positive sign left over after having taken the derivative is if that cosine were negative. But to be sure, you could always just go through and check. So I could say, okay, the derivative of -2 cosine x would be -2 times negative sine, which is positive 2 sine. So then you can go, okay, so this is right. This should be -2 cosine x plus c. Now in example 3, we're going to also use our sum and difference property of integrals. So I'm going to recognize that I can split this up into 3 integrals. And I'm basically going to use a power rule in each one. I can also take this constant out. So this is 3 times the integral of x to the 4th minus 5 times the integral of x squared and then plus the integral of x. So I was able to separate each piece across the subtraction and addition. So I can just add and subtract the integrals. And each of these constants I could take out of their own separate integrals. So the 3 can go out, the 5 can go out, and just multiply to that antiderivative. Then for these powers, I'm just going to go ahead and use the power rules for these, because this is x to the positive one, so I can use the power rule for that, the reverse power rule. So this will be 3 times x to the 5th over 5 minus 5 times x to the 3rd over 3, right? And I'm adding 1 to the power and then dividing by that number, and then plus x squared over 2. So you always end up dividing by the power plus 1. So then if I simplify that a little bit, it's 3/5 x to the 5th minus 5/3 x cubed plus 1/2 x squared plus, don't forget to add c, constant of integration. And there would be our antiderivative of this function. This is the function that if I took the derivative of it, would give me this. Why don't you try this one here? Okay, so for this one, you might have looked at that power of 2 and thought, is there a chain rule for integrals yet? Is there a multiplication product rule for integrals yet? Well, that is coming. There are ways to take the integrals of products and composition of functions, but we are not there yet. So what we'd have to do here is FOIL this out. FOIL this out so that we could get it to be just a bunch of sum and differences of different terms, because I can split my integral over subtraction and addition. Like that is allowed. But I can't split it over multiplication or at this point use a chain rule, okay? So we're FOILing this out and we're just going to integrate each term separately. So once I get it down to just a string of pluses and minuses, then I can sort of split that integral up over each of these things separately and use the power rule for this one. So add 1 to the 4 and divide by that. Power rule on this one, so add 1 to the 2 and divide by that and just keep the constant, right? That just kind of gets kept there. And then the antiderivative of a constant, this is 1, would just be 1 times the variable of integration, so 1 times t. And then don't forget to add your constant of integration. So this is the function that if I took the derivative of it would equal this, t to the 4th minus 2t squared plus 1, which if you factor it equals t squared minus 1 squared. Now in example 4, again, you're looking at this going, okay, so is there like a quotient rule? And no, there isn't. So what we'd have to do here is understand that, well, my denominator is a single term. So I can split my numerator over that common denominator. And that's what we're going to have to do here, because we have to get things in terms of addition and subtraction. And then maybe simplify a little bit, because I can cancel out 2 of these x's here. So I get just x to the 1st there, and then plus 3 over x squared dx. And then I can just do an antiderivative of each of those. I can split that integral up over those two. So integral of x plus integral of 3 over x squared. So this one is a positive exponent of 1, so I just add 1 to that and get 2 and divide by that. This one can be rewritten as x to the negative 2. So I can go ahead and use my power rule on that, because it's not negative 1, it's negative 2. So I just use a power rule. I add 1 to it and divide by that, which is just negative 1. So 3x to the negative 1 over negative 1. So that's just 1/2 x squared minus 3 over x, right? X to the negative 1 still brings it to the denominator, to the first power. And then plus c, my constant of integration. And there's my antiderivative for example 4. In example 5, again, it's got this quotient, but we don't have a quotient rule, but I could think of this one as sine over cosine times 1 over cosine. This one would be a product, right? Sine over cosine times 1 over cosine, because that's the same thing as sine over cosine squared. Sine times 1 is sine, cosine times cosine is cosine squared. So you might be wondering, like, why? Well, because sine over cosine is tangent, 1 over cosine is secant. Maybe I'll rewrite it the way we're more used to seeing it. So this is the same thing. So sine over cosine squared is the same thing as secant times tangent. Why is that important? Because we know what this is the derivative of, right? This is the derivative of secant. So secant is the antiderivative of this. The antiderivative of secant tangent would just be secant x plus a constant. And that is our answer for example 5. So I just have a couple more here that I would like you to try. So go ahead, pause your video, give it a try, and then check with the answers. All right, for the first one, we can recognize that this is just being separated by addition. So I can split the integral up over addition. And notice the variable also changed. Right now we are taking the antiderivative with respect to theta. So theta is like our x. So this is theta squared. So I would just add 1 to the power and divide by it. So theta cubed over 3. And then we have to remember that the derivative of tangent is secant squared. So therefore, the antiderivative of secant squared is tangent, or tangent is the function whose derivative is secant squared. Therefore, it's the antiderivative of secant squared. So that's kind of just by memory, and then you add your constant of integration. For the second one, we would want to first split our numerator up over our common denominator. So we have x over rad x plus 1 over rad x. At that point, it kind of helps to remember that rad x is just a power of 1/2. So I have x to the first divided by x to the 1/2 plus 1 over x to the 1/2. And then when you're dividing same bases, you can subtract their powers. So since this is division, I'm subtracting 1 minus 1/2. So that's kind of how I got to here. This was the result of 1 minus 1/2 is just 1/2. So this reduces to that. And then 1 over x to a power is just x to the negative version of that power. So my powers were positive 1/2 and negative 1/2. So then to do the reverse power rule, oh, and also I recognize this is just a sum. So I can split the integral over addition and integrate this separately and integrate that separately. So I used a power rule for both. I added 1 to the power and divided by it, added 1 to the power and divided by it, and then added my constant of integration. 1/2 plus 1 was 3/2, so I was dividing by that. Negative 1/2 plus 1 is 1/2, I was dividing by that. But when you divide by a number, you basically multiply by its reciprocal. So really I was multiplying by 2/3 there and then multiplying by 2 over 1 here. So final answer is 2/3 times x to the positive 3/2 plus 2 times x to the 1/2 and then plus my constant of integration. So that's it for this first video, and I look forward to seeing you in the next.